How's it going, Wildcats? I'm here with the springs apparatus. What we're going to do is we are going to gradually add in 5 washers onto this apparatus that's hanging from a spring. We're going to measure, or you're going to measure, the displacements each time. So I'm going to go ahead and take 5 washers and add that on. And right now we have a displacement of in the ballpark of about 1.5 centimeters. Go ahead and add in 5 more washers, so double the mass or double the force of gravity acting. So it went from 1.5 centimeters down to about 5.5 centimeters. Now I'm going to add 5 more washers. And now we're down around 10.5 centimeters. So hopefully you can pull out some information here and see if you can figure out a relationship between the weight we applied and the displacement of the spring from its equilibrium position. Alright, that's all I got for you right now. I'll pick it up on the OneNote here in a few minutes. So let's take a look at Hooke's law and the spring force. So Hooke's law says that the spring force is equal to the negative of K, which is the spring constant, times the absolute value of the displacement of that spring from its equilibrium position. So what you just saw was us hang 5 washers on a spring, and then 5 more washers on a spring, and then 5 more washers on a spring. What we could do is we could construct a graph where this was plotted on the y-axis and this was plotted on the x-axis. And then what we should find is that our spring constant would be the slope of that line, and it'd have the magnitude m, right? And that would be the spring constant. Of course, spring constant would have to have units of newtons per meter because the displacement would be in units of meters. We would need those to cancel out so that we end up with a force measured in units of newtons. Okay, so that is the start of what we need to know. Now, with Hooke's law, F equals kx, or the absolute value of the spring force equals the negative of k times the absolute value of the displacement. We need to conceptually understand that equation, right? It's simple enough mathematically. So what I have here is a ceiling drawn, and now I will construct a spring, and right now we are at the spring's equilibrium position. If we place a mass on the end of that spring, what do you think is going to happen? Well, I believe that the spring should end up stretching and eventually ending up looking like this in red. So at first we had a position here, and then in the end we had a position here. And so we had a displacement equal to x1 minus x0. And that displacement was, of course, downwards. So displacement is a vector, and right now we can see that this displacement is downwards. Okay. The spring constant is a constant, so it's just a value, no more, no less. Let's think about the spring force at this point in time. So if this hanging mass, I'll draw its free body diagram right here. If this hanging mass stopped oscillating, if we just like placed it on the spring and then gently lowered it to about where it was gonna be balanced, and then released it, and it wasn't moving, then we could say it was in static equilibrium. It's not moving and not accelerating. The free body diagram for it we could draw would be mg downwards, and then there's a spring pulling up. Instead of tension, you can imagine if this was a string, there'd just be tension in the string oriented in the upwards direction. Now we have a spring and the spring force acting up on the mass. And in this case, the spring force would be equal to the gravitational force, or at least the magnitude of the spring force would be equivalent to the gravitational force, because they'd be in equilibrium. It would not be accelerating upwards or downwards, so the lengths of those two vectors would have to be the same. Regardless of the situation, the spring force, what we see now, its direction is upwards. And so the only way that we can reconcile the displacement downwards with the spring force being upwards is with this negative sign. This negative sign is absolutely essential so that the spring force, and because of the relationship between the spring force and the displacement vectors. So that is the requirement there for the negative sign. Sorry about that. If we look at it a different way, okay, scroll down a little bit, give ourselves some more space. If we thought about a wall and a frictionless surface, take our spring, attach it to a mass. This will be mass M. Actually, it would not matter whether we move the mass here or out there. So if we move if the displacement vector x1 is in, then what happens to the free body diagram for the mass right here? Oops. Come on. What happens to the free body diagram for the mass right there? We got the normal force, we got the gravitational force, and now the spring would be compressed, trying to push the mass to the right. The spring force would act to the right. But if we thought about x2 over here, let's go with red. If we had a displacement to the right instead, the free body diagram out here, we would have that mg downward still. The box wouldn't increase its weight at all. We'd have a normal force acting up, giving us no net force in the horizontal direction. But now that spring is stretched, and it would try to pull the block back towards the equilibrium. We'd have a spring force oriented to the left in this case. So the direction of the displacement and the direction of the force vectors with springs is always opposite. Basically what we'll find out is that the spring force is a restoring force. And what that means is that it's going to try to restore the object back to its equilibrium position. So if the object is over on the right and the spring force is oriented to the left, it means its equilibrium position must be to the left. It's going to accelerate, it's going to pull that block back towards the equilibrium position. And then if that block kept on moving past the equilibrium position, then the spring would start getting compressed, push back to the right. It's going to try to restore it back to its equilibrium position. This starts us into a second topic, or another topic in physics, called simple harmonic motion. That's going to be when we see the mass oscillate back and forth, because we'll have simple harmonic motion there. And you'll get to see waves and stuff like that when we get into simple harmonic motion. So that is Hooke's law. I hope this helps you along the way. And that's all I got for you right now. So make it a great day or not. The choice is yours.